back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, every week, we discuss the cutting edge of science, science that touches our lives and reshapes our view of the universe. And in this hour, we're going to throw the lines open because this hour is your hour. Okay, well, without further ado, let's just jump right into the first listener phone call.
Hello, this is Jeremy, and I'm from Huntsville, Alabama, Rocket City. And I was calling to ask a question regarding photons. Could it possibly be that photons are an expression or a product of a particular movement of space, of the fabric of space-time? Could that possibly explain the wave-particle duality of photons? Thank you for listening.
Well, you asked a question that actually is at the cutting edge of, well, what I do for a living. I work on something called string theory, which we think is the theory that eluded Einstein in the last 30 years of his life. First of all, what is a photon? A photon is a particle of light. Light, we know, has particle and wave-like properties. The particle properties are manifested in photons, which are particles of light. However, as these particles move, they create electric and magnetic waves that surround the particle, sort of like the wake of a boat when the boat goes through the water. These waves give the wave-like properties of light. So is light a wave or a particle? It is a particle. But when it moves, it creates waves of electric and magnetic fields. So that explains the wave-particle duality. Then the next question, you ask a deeper question. Where do photons come from anyway? Einstein thought that maybe they were distortions in the fabric of space-time. You see, Einstein believed that his theory of gravity was so powerful that all forces could be explained as vibrations in space and time. That theory was then proposed by Theodore Kaluza around 1920, and Kaluza made an astonishing, absolutely revolutionary hypothesis that we still debate even today, and that is, if I take Einstein's equations, which are in 4 dimensions, with time being the 4th dimension, and add a 5th dimension, get this, a 5th dimension to Einstein's 4-dimensional theory, where does that 5th dimension go? It turns out that you get the equations for photons coming out. Now, this is mind-boggling. Think about it for a moment. Simply by adding another dimension to Einstein's theory of gravity, which is defined in 4 dimensions, out pops out a theory of photons. So this is called the Kaluza-Klein model, and we actually use it in string theory. In string theory, we actually go to 10, maybe even 11 dimensions. And what is light? Light is distortions in a higher dimension. And so this is a new reinterpretation of Einstein's equations that incorporate light. So again, what is light? Vibrations in the 5th dimension. And so you begin to realize that time and space are sort of like the surface of a pond. Think of a pond. Ripples can form on the surface of the pond. The pond, of course, is 2-dimensional, but you have 3-dimensional ripples on the surface of a 2-dimensional pond. And these ripples have a life of their own. And what do we call them? Photons, or light. Now, on Star Trek, you have something called photon torpedoes. So Captain Kirk says, man the photon torpedoes. Well, what is a photon torpedo? A flashlight. Because photons are nothing but particles of light, and a photon torpedo would be a flashlight. So to answer your question, yes, the latest theory is that light is vibrations in the 5th dimension, a dimension that we cannot see, but a dimension that causes ripples on the surface of the pond, which is space-time, and the ripples create shadows. We can see the shadows. And what are the shadows called? Light. So that resolves a lot of the paradoxes of gravity and light. Now, is this correct? Can we prove it? And the answer is no. At the present time, we do not have machines powerful enough to test this theory. However, if you want to know more about it, get a copy of my book, Parallel Worlds, where I discuss the Kaluza-Klein theory and attempts to one day prove it. Okay, let's move on now to the next listener phone call.
Hello, my name is Jordan Smith. I'm calling from Oakland, Maine. And my question is, you mentioned on a talk at Google that there are 3 levels of societal development as humans, and right now we're at phase 0. And in 100 years, maybe we'll be at phase 1. And my question is, do you think we have been visited by any advanced beings that you've hypothesized? And if so, do you think we've interpreted these visits as encounters with God or gods, demons, and angels? Also, do you think we can achieve dimensional travel using our minds in the distant future?
Well, one of the people who really pondered this question was Carl Sagan. In fact, Carl Sagan wrote in one of his books that if our ancestors were to have encountered an extraterrestrial civilization landing in their backyard, what would we think of them? We would think of them as gods of some sort. And then Carl Sagan said, well, he doesn't know for sure whether we've been visited or not, but it does make you reflect on the primitiveness of our own civilization. And as you mentioned, we physicists rank these civilizations in outer space by what is called the Kardashev scale. Nikolai Kardashev was a Soviet astronomer, and he was frustrated when people talked about aliens in outer space. They would only talk about little green men and things like that. And he was a physicist. And we physicists rank things by energy and information. That's how we rank objects. And so he said, let us rank alien civilizations in outer space. He called them Type 1, Type 2, and Type 3. A Type 1 civilization is planetary. They can harness all planetary forces. They can control the weather. They can alter the course of rivers. They can begin to think about modifying volcanoes and earthquakes. Any planetary energy they control. Type 2 exhausts the power of a planet, and they start to use the power of their sun. In fact, they absorb all the energy coming from the sun. They can even encase their sun with a sphere to absorb all its energy. And then Type 3 is galactic. They can roam the galactic space lanes with their starships. And to compare it with science fiction, a Type 1 civilization would be like Flash Gordon or Buck Rogers, able to catapult themselves anywhere on the planet. A Type 2 would be Star Trek. The Federation of Planets, if you follow the series, can only manipulate planets within what is called the Alpha Sector, a small sliver of the Milky Way galaxy. Then there's Type 3. Type 3 would be like the Empire of Star Wars or the Borg. The Borg of Star Trek is a Type 3 civilization, and they can eat Type 2 civilizations for breakfast. In fact, on Star Trek, that's what the Borg wants to do, absorb all the technology of a Type 2 civilization, the Federation of Planets. Now, on this scale, what are we? Do we manipulate the weather? Do we play with the stars? Do we play with black holes and roam the galaxy? No, we're Type 0. We get our energy from dead plants, oil and coal. However, if we were to visit or be visited by an alien civilization, what would they be? Well, if they can go between planets and stars in the galaxy, they're probably a few thousand years ahead of us in technology, putting them in the realm of Type 2 or more than likely Type 3. So if we were to meet a Type 3 civilization, we would consider them to be gods. For example, if you were to meet somehow your grandparents right now, suddenly talk to your grandparents, they would think of our life today as the life of a sorcerer, a magician, able to reach the moon, able to communicate instantly with anybody on the planet. They would think of us as sorcerers. Now, if we were to meet our grandchildren in the future, let's say in the year 2100, they would become Type 1, and we would consider them to be gods. So you begin to realize that technology is relative to your development. As Arthur C. Clarke once said, any sufficiently advanced civilization is indistinguishable from magic. So if we were to meet a Type 3 civilization, we wouldn't even know how to communicate with them. First of all, they would probably telepathically communicate with each other. We already are on the verge of mastering telepathy. We can now codify and digitize brain patterns, send them on the internet, decode them, and telepathy is actually a possibility. For example, the military has been pioneering this technology. The military has had veterans from Iraq and Afghanistan, and they have spinal cord injuries, severe injuries which leave them paralyzed. You can put a chip on the surface of their brain. That chip is connected to a computer, connected to a laptop, connected to a wheelchair or a mechanical robot. So by thinking, just thinking, you can manipulate your wheelchair, turn on the light, turn off the light, get any email message, download a movie, email your parents, and these people are paralyzed. They are trapped in a motionless body, and yet mentally they can control the internet. And if you can control the internet, then by golly, you are almost human. And so you begin to realize that if we were to meet a Type 3 civilization, we wouldn't even know how to begin to understand their wants, desires, their goals. They would be thousands of years ahead of us in technology, and they wouldn't even communicate the way we communicate. They would probably use BrainNet. BrainNet, which I write about in my book, The Future of the Mind, is the internet that is using thoughts to communicate rather than digital signals of zeros and ones, zeros and ones. So the question is, when will we become Type 1, Type 2, or Type 3? Well, Kardashev said that if society develops at, let's say, 3% a year, that's a modest economic growth rate. And if we were to expand at roughly 3% per year, we would become Type 1 in about the year 2100. In about 100 years, we'll become a planetary civilization. We'll become Type 2 in about a few thousand years, and we'll become Type 3 in perhaps 100,000 to 1,000,000 years in the future. And you know something? We can see the beginnings of that right now, even as we speak. For example, a planetary language. We are witnessing the birth of a planetary language. The two languages most common on the internet are English and Mandarin Chinese. Also, we're beginning to see the beginning of a Type 1 culture with the internet. The internet is the first Type 1 technology to fall in this century. We are privileged to be alive to witness the birth of the first Type 1 technology, which is the internet. But you can also see that in culture. We're witnessing the birth of rock and roll and rap, the beginning of a Type 1 music, the beginning of the European Union, and different kinds of trade blocs. Of course, these change all the time. But yes, trade is becoming international, planetary, in fact, planetary like a Type 1 civilization. We're seeing the beginning of a Type 1 high culture like Chanel and Gucci and the different kinds of expensive handbag manufacturers. And so the point is that we can see the beginning of a Type 1 civilization right in our own backyard. And we will reach Type 1 status probably by the year 2100. Okay, let's move on now and take the next listener phone call.
Hello, Kaku. This is Gary from Frisco, Texas. I had a question on black holes. Number one, I was wondering, since there's so much mass in a black hole, does Einstein's equation still hold true with the energy that's in a black hole? And what is the temperature of a black hole with all that mass there? The other question on the black hole is, since it does, light cannot escape the electromagnetic wave, do gravitational waves escape from a black hole, or are they pulled in also like an electromagnetic wave? Thank you very much.
Okay, well, you had some very interesting questions. First of all, Einstein's equations do predict the existence of black holes, and we actually see them now in outer space. We've lashed together 5 radio telescopes scattered around the planet Earth and actually photographed the event horizon of a black hole. Well, let's take a short commercial break, and after the commercial break, we'll talk about can you escape a black hole, and was Einstein wrong about some of the features of black holes? Welcome back to Science Fantastic with Professor Michio Kaku. Well, the lines are open. You're going to get right to us. Well, we had a question that came in. Was Einstein wrong about some of the features of a black hole? And the answer is yes and no. First of all, black holes come right out of Einstein's equations. Einstein's theory was proposed in 1915. 1 year later, in 1916, during World War I, Karl Schwarzschild, a German physicist, found the first major solution, exact solution of Einstein's equation, which became the black hole. However, the black hole had so many bizarre properties, so many crazy aspects to it, that Einstein thought that yes, they are solutions of his equations, but they could never form naturally, that a star, a swirling mass of hot gas, would never condense into a black hole. That very same year, in 1939, Robert Oppenheimer, the man who created the atomic bomb, actually found a way to create a black hole using Einstein's equation. He said, forget about swirling stars and stars that are spinning. What about a star that implodes? A star that collapses under its own gravity because it's so massive. And he found, bingo, yes, a collapsing giant star could in fact become a black hole. Now, once you fall into a black hole, then you ask yourself a question, what lies at the center? Einstein's equations say that at the very center of a black hole, gravity becomes infinite in intensity. Well, that's ridiculous. I mean, infinity is an excuse to hide the fact that you don't know what you're talking about. So you see, Einstein's equations are fine. They work for black holes. We test them with black holes. But at the very center of a black hole, Einstein's equations go berserk. They blow up on you. And so we still don't know what lies at the very center of a black hole. In 1963, mathematician Roy Kerr found that if a black hole was spinning, not stationary but spinning, it didn't collapse into a dot at all. The textbooks are all wrong. There's not a dot of infinite density at the center of a black hole. What is there at the center? Well, according to the equations, there's a wormhole, a gateway, a passageway to another universe. Now, this is where Einstein's equations begin to break down. We don't know for sure whether or not wormholes exist. But yeah, if you solve the solution for Einstein's equation, there is a gateway, a doorway, a passageway, a subway system cutting across space-time called a wormhole. Now, how do we finally resolve the question of what lies at the very center of a black hole? That requires a theory higher than Einstein's theory. We need a new theory, and the only theory which can do that is called string theory, and that's what I do for a living. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. You can give us a call at 612-564-8135 and ask that question about science. Leave your name, call letters to the radio station or website you're listening to, and the city you're calling from, and maybe your thoughts that can be heard on the internet and 100 radio stations that carry Science Fantastic. Well, just to conclude, we had a question about black holes before the break. The question was, well, can gravity waves escape a black hole? And the answer is, if a gravity wave comes directly from the black hole, the answer is no. It's trapped, just like light is trapped. But you see, swirling around the black hole is something called the accretion disk, which is clearly visible by our telescopes. It looks like a gigantic flying saucer, swirling gas swirling around the black hole. And that's where gravity waves can escape. In fact, we have something called LIGO, which is a gigantic gravity telescope. It's based in Louisiana and Washington State, and it can actually detect the radiation from colliding black holes in outer space. When two black holes collide, they release the most titanic source of gravity waves in the universe, which is now being picked up regularly by LIGO detectors. And so once again, Einstein's theory comes out giving a prediction that is being verified with some of the largest machines of science in Louisiana and Washington State. LIGO, gigantic laser interferometry antennas that can detect the collision of black holes billions of light years in outer space. Okay, well, let's move on now and take the next listener phone call. Hello, you're on the air.
Hi, this is Ed. I'm calling from Wilkes-Barre, Pennsylvania. WILK, Professor, love your show. It's the best. Listen to it all the time. There's two quick questions. Just heard the average cumulus cloud weighs an average of 1.1 million pounds. It blows my mind. How does it float in the air? And when you arc weld, you create an electromagnetic field. If you weld near a magnet, the arc goes wild. Is it possible to arc weld near a magnet? Thanks so much. You're the best.
Okay, well, let's take these questions one by one. First of all, why do clouds float? Well, we have to ask a simple question. What is a cloud made of? A cloud is made of tiny microscopic droplets of water vapor. And how much does water vapor weigh? Well, pretty much the same as ordinary air. And that's why water vapor can float. And when you see a cloud, you're looking at the condensation point, the point at which water vapor will condense into tiny droplets of water. And so that's why clouds can float, because they don't weigh much. However, when you add it all up, then, of course, the total amount of the weight of water vapor could be enormous. But water vapor by itself can float. In fact, it was Archimedes who actually worked out the criterion for what can float and what can't float inside the air or water. It turns out that if there's a buoyancy force keeping objects afloat, and the buoyancy force is equal to the weight of the displaced water. That's why objects can float. Now, if you think about it, a battleship is much denser than water vapor, but a battleship does not sink. Why is it that a battleship made out of steel can float in water? And the answer is, the battleship is basically hollow. So most of the volume of a battleship is air. Just like in a cloud, most of it is water vapor and air. Battleships can float for the same reason. The fact is that battleships are hollow, and that's why the displaced water exceeds the weight of the ship itself, and that's why battleships can float. Also, when you take a look at arc welding, you're heating gas to the point where it becomes a plasma. That is, it becomes ionized. You're ripping the electrons off the atom. Now, the atom is basically electrically neutral. However, if you start to heat it up, you can ionize the gas. And ionized gas is quite dangerous. It can glow. That's what you create in a plasma torch. And once it's electrified, then, of course, is magnetic as well. And therefore, a plasma will be distorted by the presence of a magnetic field. So watch out. Your plasma could do all sorts of strange by gyrations if it's in a strong magnetic field. I wouldn't do that. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. So let's move on now and take the next listener phone call.
Dear Michio Kaku, this is Mukesh. I listen to the podcast Scientific Fantastic. I am calling from Phoenix, Arizona. Myself and my family all are great fans of yours. I read your book, Hyperspace, in my college days, and since then, it truly inspired me, and I'm a great fan of yours. Sir, my question is, you and other scientists often talk about space and time are together, like a space-time fabric. They are not separate to each other in true sense, right? So in the movie Interstellar, the dad communicates with his daughter from a future to the past using gravity waves. So my question is there any reasoning which you can provide that gravity waves can come to us, reach to us from a future or from the past, without affected by the time, right? So looking forward for your answer. Thank you, sir. Have a nice day.
Okay, well, the movie Interstellar was a great movie, and the people who consulted for it were physicists. And so it is the only film that I know that is, quote, scientifically correct. In fact, one of the physicists who consulted for the movie, Kip Thorne, would eventually win the Nobel Prize for working on gravity waves. And if you saw the movie, it gets really bizarre toward the end of the movie because we start to leave the world of Einstein and enter the world of string theory. And string theory is defined in higher dimensions, dimensions beyond the familiar dimensions of length, width, and height. We're talking about dimensions up to 10. And in the final scenes of the movie, Matthew McConaughey is floating inside a four-dimensional cube called a tesseract. A tesseract is an unraveled four-dimensional hypercube, and that's what he's floating in the final scenes of the movie. And then he communicates with his daughter in another time era. Now, how do you do that? You have to use a wormhole. In other words, a gateway between different points in space and time. And it gets speculative, of course, because string theory itself is not fully understood. But that's what he does in the final scene. He communicates with his daughter across space and time. And then you ask a question, can gravity waves do that? Well, the short answer is no. But if you could open up a wormhole that is a gateway through the fabric of space-time, then the answer becomes maybe. So what is a wormhole? If I take two parallel sheets of paper and I drill a hole through both of them and put a pencil through these two sheets of paper, they're now connected. So that if you spend your time on the top sheet of paper, one day you might fall in through this hole and wind up on the bottom sheet of paper. Well, the link between the top and the bottom sheets of paper, that is the pencil, is the wormhole. The wormhole was first proposed by Einstein himself in 1935 with Nathan Rosen, and they're called Einstein-Rosen bridges, a bridge between two universes. And we know that a black hole, a spinning black hole, is perhaps the simplest example of a wormhole. That is, the black hole does not collapse to a dot, it collapses to a ring. And if you were to fall through the ring, you fall through the wormhole to another universe. In fact, if you fall through the ring twice, you fall through yet another universe. So it's sort of like the elevator button on an apartment building. You have all these buttons, you push a button, and you wind up on different floors. Each floor is a universe, but the whole collection of them is the multiverse. So these are solutions of Einstein's equations, but of course that doesn't mean they're real. The final theory is string theory, we think, and string theory unfortunately is so complicated that we do not yet know the answer of whether or not you can, like Matthew McConaughey, talk to your daughter in a different period of space and time. So to conclude, we have Einstein's theory, but Einstein's theory breaks down at the center of a wormhole. We have to use string theory at that point, but string theory is not yet developed enough to answer the question, can you then talk to someone in the past or future using a wormhole? We're not quite there yet. Okay, well, let's move on now and take the next listener phone call.
Yes, Professor. My name is Roy Martinez. My question is about the ISS station where the astronauts are going around in circles up there. What's powering that vehicle? Because does it ever run out of fuel? or is just nuclear power? I'm just curious. How is it going around so fast around the Earth's atmosphere? So what's firing? Thank you very much.
Well, you ask a great question. Some people ask another question. If our space probes can go all the way out past Pluto, then where does the gasoline come from? I mean, where does the energy come from that allows our space probes to go way out there past Pluto and even leave the solar system without any gasoline whatsoever? And the answer is, well, there's no friction out there. Empty space has no friction, and Newton's first law says that once you're in motion, you can stay in motion forever. And so that's how our space probes can reach the farthest reaches of the solar system. There's no friction. They simply coast the way like an ice pick, like an ice puck on ice. Well, that's it for this segment of Science Fantastic.